Good afternoon. Welcome to Lecture 5. This is Camille Corchism, your instructor for Packaging 450. Today, we are going to continue on Chapter 2, which deals with program management and returnables, as well as looking at the homework from last week. So we're going to go over homework number 1, the answers, and I'm checking those as we go, so you will see them all checked by the end of the week. Again, if you have any questions for chapter 2 as you read through it, let me know. The homework will be posted for chapter 2 for assignment number 2. That will be posted by tomorrow morning. And again, it will be due Monday at 10 a.m. Eastern Standard Time. So first, what I wanted to do is share my screen and just go over a few of the concepts to just kind of talk about what we went over yesterday with chapter 2, the beginning of chapter 2. We're talking about the program management process and making sure from a packaging standpoint that you are proactive. First and foremost, we talked about the different phases. So phase 1, looking at it from, we talked yesterday about what the activities are during the first phase. I think they even refer to as phase 0, but it's the first phase. That's why I listed it as phase 1. But with that being said, think of this from the standpoint of a packaging engineer. When we talked yesterday, we talked about the broad program as a whole versus where the packaging engineer falls into it specifically. So again, the first one is the concept. We talk about the very first phase where the finance team and the program management team is talking about a new vehicle. Like I said, do we want an SUV that can also, to go on water and fly in the air, and EV, those are all the things they talk about. From a packaging standpoint, you're looking at how to leverage packaging, what parts are going to be existing or similar, and we'll use the same packaging, and then what is going to be brand new. And what's going to be brand new, how do you estimate that? You're really looking at capital budgeting, really, or planning and forecasting what that is, because again, the returnables are considered assets. So they're treated the exact same on the books from an accounting standpoint as a piece of equipment that, on a conveyor line or a piece of equipment in the plant. So it's dealt with the same way. So you have to put together a plan, explain exactly what it is that you are looking at doing. And when I say exactly what you're doing, from a standpoint of how many containers you think you're going to need, what the cost to develop those containers will be, like we spoke of yesterday, and then put that together in a budget. Like I said, many times the program team in finance will, make up their own estimate. And sometimes they will base it on the cost of the part, and they'll just take a flat percentage of that, which if you have a small electronic component that's very expensive and you take 5% of that, the cost of the packaging is most likely not going to be consistent with that. And then if you have, say, a very large part that's heavy but pretty durable, and it's a commodity, so it's not very expensive, it might end up being so large it ends up in a bulk bin or rack. And now you're looking at something that costs $100 or $200 for a pack, or even thousands of dollars, and 5% of the part or the number of parts that are in that pack won't, would be, it wouldn't be sufficient. So it's really important from a packaging standpoint that you do get involved and look at what you think it's going to cost and have a really good idea for that. So again, that's the first phase. The next phase, you're looking at understanding the product. You should have a better idea of what parts are going to be in the vehicle or the assembly or whatever parts you're supplying. If you're at a tier, you should have a good idea of what the general parts are. Again, you're separating it from, we're leveraging existing parts, and we know that this part is, it's sensitive to shock, or it's sensitive to moisture, or it's sensitive to scratching. You understand what the packaging needs to protect from, or maybe shipping shipping on a boat or a barge and overseas. And, so you kind of understand, get a general idea of the hazards for the known. For the unknown, you are looking at what are the risks, what does the packaging need to do to protect, display, dispense, transport the part effectively, safely, and at a cost that's in line with the program. If you are doing this on a regular basis and you work a lot with your program management team, they will start to rely on you and lean on you for that information, versus coming up with a percentage number and using that across the board. It'll be a much more accurate piece of information. And again, you can also figure out, which parts are going to be a risk for packaging that you need to package for. You want to get to the point where you have so much information on previous programs and what's coming down the line for new parts, that you're managing by exception. So you're really looking at developing innovative new packs for, new parts, or parts that have been known over time. They've proven to be difficult to pack, and they require a lot of protection. So you can focus your time on those versus looking at everything. You can start to narrow down. The next one is, the next phase, you're looking at designing or getting ready for launch. So you're planning for that launch. You need to know, how many containers you need, if it's returnable, which containers are going to be expendable, making a reasonable estimation on, which ones are best in an expendable pack. So something's overseas, or, something that is, getting stuck at a customs border, those are some of the things you might want to look at. Also, at this point, you're looking at working with the suppliers of the parts, as well as packaging suppliers. Generally, most companies in automotive will have packaging suppliers that they tend to rely on and go to, and have a really good feel for their parts and the history. So you can start working with those suppliers at that point to get packaging prototypes, also part prototypes. This is probably a really good time, even as early as phase 2, I would say, start telling people you need product samples for testing and confirming sizes, and taking it to a test lab and doing some transit testing. So you want to start letting people know that in phase 2 that you're going to start asking for part samples for your packaging. And then in phase 3, you'll actually be getting prototypes of your packaging. Again, this is when you have the opportunity to start running tests, and they'll be testing the product. This is your chance to get in and test the packaging along with it. So at this point, you probably will have prototypes. You may have some that are close to production quality. You may have some where you've taken an existing tote or bin and you've modified the dunnage to meet the needs of the new part that's coming in. But at this point, you're testing, you're checking, you're starting to look at what opportunities are there, which ones are the exceptions that you're managing. And again, getting prototype parts as well as packaging. And then the next phase, you're looking at prepping for launch. You are, at this point, you're running final testing, you're doing validations, you are approving packaging. So you approve the ones that are fine and work, and you're focusing on the ones that you may still need to tweak, confirm, and do a final test for. Another thing is that, by this time you should be getting your packaging specifications from your suppliers. They should be able to tell you what kind of packaging they're looking at, what kind of dunnage it is, and you at this point would be approving it and saying, yes, this meets our criteria. Because again, there are so many parts that many times your packaging, your product supplier is going to submit a proposal of what they think their packaging will be. Many times they already have standard packs that they use. If they don't, you want to drive them towards having your standards. So if you start looking at company standards, which I talked about before, the importance of having company standards, really, really important at this point, because then you can start driving your suppliers towards approvals based on your company standards for what you require for incoming packaging, whether it's expendable or returnable. One of the other pieces of information, I think I mentioned this before, is a PPAP, which is a quality process where they are going through all of the elements of the part and checking off saying that it's ready. So it's like a pre-production approval process. And what they do is they'll have a long checklist and say, has this been run? Have we done this build? Has it passed quality? All these things for the parts. But then there's a section on packaging. Do they have the packaging? Is it complete? Has it been tested? Does it work? Does it meet our standards for packaging? And does it protect the parts according to our company standards? Some companies, they will go through and the quality team will go through and try to check all these things, and then they'll get their own pack in, and then they'll run their own test, and then they'll say, oh, we have some questions or might have a delay, because they will, I've seen it where companies are working on their PPAP. The quality team will be a separate team. They work a lot with manufacturing and making sure that if there are any quality issues with the product, that it's taken care of. It's, they do root causes and they resolve the issue. But one of the other things that they do is they will take the corrugated boxes and they will go with the caliper and they will measure the thickness of the corrugated. I'm trying to find an example. They will actually measure, sometimes they'll measure the corrugated and then they'll say, does this meet the spec? We noticed that it's thicker in some spots than other spots. And because they don't use packaging standards, they don't understand that if it's B flute or C flute or 275, that is the standard for packaging that it needs to meet. And the transit testing that is done, and material testing, if necessary, that's done, or certification that it meets some material specs for ECT or burst, that's what's needed. So it's important too that at this point, that when that PPAP is done, that you can present to your quality team, these are the packs that we're looking at, and from a packaging standpoint, I've signed off on these and they meet packaging's requirements and standards. Again, back to making sure you have standards, because if you have formal written standards for what your packaging is going to be for your company, when the quality team does their approval process of the PPAP, they're basically just checking off that yes, packaging has signed off on it and meets all of packaging requirements. And that will reduce delays, because sometimes this can delay a launch and you don't want to delay a launch because the quality team is measuring the thickness of a corrugated box with the caliper and saying that they don't know what it's supposed to be. So I just want to mention that the importance of making sure you have specs and documented sign-offs of the packaging of each pack, every single part for this program, every single part for this vehicle, or the part of the vehicle that's going to the assembly plant. Whatever you're packing out, everything that's packed and shipped to whoever your customer is. If you're on the supplier side, you have to make sure that you have a sign off, and the sign off will include packaging, the sign-off might include quality. Every company is a little different, but you would have a group of people that review it. Someone in manufacturing, for example, all these people review it and sign off on it. And then after that, once you're launched, you're just really managing, making sure that containers, the returnable containers aren't disappearing, also making sure that things that were designated and specified in returnables don't start showing up permanently in expendable packaging. You want to make sure that the expendable packaging that was approved and planned does not change at some point during the manufacturing process, during the life of that vehicle. And this is also a good time to look at, how much was spent on this program. And there's going to be some loss of returnable packaging for whatever reason. There may be some design changes. You may have a pocket of theft. You may have volume increases. There are just a lot of reasons why you may have to revisit the packaging throughout the program, which is usually going to be 5 years. So you just want to make sure that you stay on track. You're not losing containers, or you don't need more containers, and you don't have containers that are broken. Those are things you might want to address. If you find that you have a lot of damage to containers, maybe a redesign or modification of that packaging is needed. And then you'd have to work on blending that in, transitioning to that pack. If you need to rework existing packaging, you have to come up with a plan on how to do that without interrupting production. So something similar to that rack process that we talked about in lecture 4 on how they're building so many racks. So not so many that they're flooding the building and they can't fit in the building, but they're making enough and within a certain time period to keep production running and keep the supply chain full of the packaging. The next slide that I have is a slide of basically the same process that I talked about, but I wanted to talk about how the packaging development process aligns with the program management process. So you'll see the phases and the different areas and designations of what those different phases are. So basically, it's because it's really important to align your activities in packaging with the program management team so that you're in sync. So the chart that you see illustrates the alignment of those activities, and you're going to be working with cross-functional teams during that whole process. So for example, you're going to work with purchasing to make sure that the suppliers that they use for packaging are approved and in line and they have the right pricing. But you also will be working with purchasing and maybe even what's called the commercial team, because the suppliers are going to be giving you packaging proposals. So you have to know when purchasing is officially giving contracts to those part suppliers so that you can start working with them immediately and make sure the packaging is meeting the standards and requirements of your company, whatever you've designated from a packaging team standpoint. Also, by incorporating these packaging processes into that launch and program management cycle, it really helps you with efficiencies related to cost, delivery, timing, and design. So as you go through automotive, you'll see there are KPIs, key performance indicators, and a lot of them are revolving around things like cost, delivery, and timing. So those things are related to performance, on time, the right amount, keeping in line with cost, all those sorts of things will tie together. So by incorporating your packaging process into the program management processes at the time of certain gates and phases, you'll be more efficient. So in this chart, again, you're going to see the function for packaging, what packaging is doing. And then you're going to see, these circles are called gates in the program management process. These are decision points. So what they'll do is they have activity, and then they get to this point and they say, okay, so do we have everything we need? Does this look good? Is this viable? Okay, then let's make a decision as a team that we're going to move forward. Or do we need more? Maybe it's not working. Can we recover and fix this? Or do we need to just, fold this product or project and move on to something else? So at each one of these gates, this is a decision point. Another thing that you want to know is that, these are the phases that occur. These are the activities that occur during the launch. And then these are the functions of packaging. These are things that you'd be doing from a packaging standpoint. And then these would be inputs of information that as a packaging engineer, you would be receiving. And then these would be the outputs from a packaging engineering standpoint, what you might be giving to the program management, someone within that program management or launch team. So for example, we will go to phase 3. This is usually one of the most active phases, but design and test. You are looking at doing, working on designs for packaging, working with suppliers to make sure the designs are matching the requirements, getting prototypes of packaging, prototypes of parts, be doing testing. And then this is another thing is called an FAI, which is a first article inspection. So that is just another opportunity to look at the packaging with the part in it. The engineering team, the program management team, they look at the FAI as an opportunity to approve a part, or you're getting closer to approving a part. But for the packaging issue, this is your chance to have the part that's pretty close to being production ready. If it's not already production ready, it's really, really close. This is the opportunity to put your part in your packaging and make sure that it fits, it works. If you need to do lab testing, this is the time that you want to make sure lab testing is scheduled, and you want to make sure well ahead of time, like I mentioned before. Back in phase 2, even if they're talking about business cases, you want to start saying, I'm going to need parts. So at this point, you can get parts and you can make sure that things are done. So some of the inputs, like I mentioned, would be, you would be receiving prototype parts, you'd be receiving prototype packaging, and you would get transit testing done. At this point, outputs would be, test results. So, you're running testing with these prototypes, and you'll get test results at this point. So this is where you're saying the parts were okay after the transit testing, or maybe we need to make some revisions. But you want to, make sure that the parts pass transit testing that is consistent with whatever transit is going to be used. So whether it's trucks or trains or boats or planes, whatever it might be, you want to make sure that your transit test reflects how things are really going to be shipped. Next, an example, let's see for phase 4. This is where you're prepping for launch. Your everything's being approved. You're, kicking off purchase, or purchasing is kicking off purchase orders, but they'll do this based on the fact that you have approved packaging. So here you're going to get samples of what's called production intent packaging. And that's where you'd validate it and do the final approval. So this would be your final opportunity, get the parts in. The parts are going to be very, very close to production, if not production. And then you will take your packaging that it's actually it's more defined than a prototype, and it's mimicking the production as closely as possible. Say if for some reason you can't get the production yet because it's, you need higher quantities, this might be where you might get a prototype mold, instead of, prototype tooling for a mold, instead of a full-blown mold. Before you spend $100,000 on tooling for an injection molded part, you would have a prototype mold put together, and it's going to look and feel and act a lot like your final production. It's only that it's a mold to make lower quantity. So instead of making, thousands or hundreds of thousands, whatever it is that the program requires, you can just, make just enough for these test runs. Your input would be a production intent pack, very close to what you are planning to ship. And your output would be packaging approval. So whatever approval process your company has set up, part of your work is making sure that everything's signed off. If it's not signed off, understand what the issue is. Did it not pass testing? Does it not fit line side? Maybe it's the wrong size. Maybe it's hard for operators to get the part out of the packaging. Whatever that issue might be, this is the final chance to really work it out before it's approved. And another output would be information showing that it's approved so that the purchasing team can start putting purchasing orders together so that they can purchase a packaging, and then the supplier can start making the packaging. So at launch, the amount of packaging that's needed to start the launch is available. So again, going back to that example on the racks, where they're not getting all the racks made at the same time, but they're going to meter the racks in measured amount and ship them in on a schedule so that it means production, but it doesn't flood the plant where they don't have enough room to store it, but then it doesn't shore up the plant either, so it slows down their production. Couple things that I wanted to mention would be that, I mentioned what those gates are, that they're decision points. The phases occur, like I said, between those gates that are showing with the circles, but they, again, have specific activities. That's where I talked about, you have your functions, but your inputs and your outputs, all these are really pieces of information or activities. They will all have timing associated with it. So if you know that it's going to take, 3 months to get tooling, or a month to get material, or, it's going to take a week to get a test, all those things go into play. And then, you also will either be responsible for those activities, or someone will be responsible for those activities. And the program management team keeps track. I mentioned the Gantt chart that is a combination of a spreadsheet and a timeline. One of the other pieces of information they'll have on that Gantt chart will be who's responsible. So for all of the packaging related activities, generally it would be the packaging engineer. Things like putting in purchase orders for the packaging, like here for a packaging purchasing deployment, that would be more than likely someone in purchasing, but you may have some responsibilities as far as giving information to purchasing so that they know they have to go ahead to buy the packaging. I'm trying to think if there's anything else I listed and mentioned on here that would be important. I think that's really it. If this is not clear when you see this, feel free to shoot me an email. Feel free to, join me on Friday in the office hours, or schedule a separate office hour. Most of this really won't be in the homework. This is more of information for you to know, because once you get into, if you're going to work in automotive packaging and you start working, these are really good pieces of information to know. All this does, it makes sure that your packaging is approved on time, and it allows for time for the packaging to come in on time and be delivered in time for production of the product. It also gives you some time and cushion, because if you have this level of organization and you work with the program management team on packaging, it gives you time to manage by exception. So you can anticipate which packs are going to need the most attention. for example, sensitive parts, or maybe you have a supplier that's having supply chain issues. You can accommodate for that. Or maybe you have a packaging supplier that's having supply chain issues. You can get ahead of that and make sure that everything that you need is in play when it's time to run your first production run and launch the new parts. Okay. This one, I just want to mention this one really quickly because this ties in. This will go, you will see this again because this really ties into the fleet calculation. So when you need to know how much packaging do you need, you've done all the other work, you've come up with the type of pack you need. We talked about, the racks, as I'm going to go back to that example again. With the racks, you know that you need to have so many racks and you're going to have to meter them out over a certain period of time. But how do you even know how many racks you need? There is a calculation for fleet that you need to do. But that also, again, ties into this whole process. Again, I just wanted to stress that it's important to align your activities and packaging with the program management teams. You want to make sure that you're involved in meetings. If you're hearing about meetings with the program management team, you want to make sure that you invite yourself and show up and let them know that you're there, part of the team, or as early as possible. They may think, oh, you're not needed at the phase 0 or the very first phase, but you should be a part of it, and offering up your information on your estimates, your calculations, your budget, what you project for your budget for packaging and those sorts of things. They may not understand it now, but they will appreciate it going forward, and then they'll start asking you for that information in the future. And another thing is, besides aligning with the program management team, you also want to align with the cross-functional team. So going back to this slide, you're actually working with cross-functional teams. So, I mentioned purchasing, right? Here, for example, you're working with manufacturing, and you might be working with the teams that develop the equipment. So, do we need lift assist? What kind of line side racks are we going to have? How much space is there at the line for the operator to have racks? That is important for you to know, because if you have limited space, that will also drive, what type of packaging you have. So if you only have 2 feet of space, something like this, a full size, that's a 48 by 45 inch bin, that's not going to fit in your window of 2 feet of space. So it's really important to work cross-functionally with all the other teams that are involved with this whole process. I mentioned before, sometimes packaging engineering is not included in the formal process. It might be considered we'll check with them and get it from them, and the packaging would just magically show up. But again, it's okay to crash the party, and it's okay to be part of the team. Show up to meetings, show up to when there are launches or build events and testing. You want to show up. You work with the engineers that are building the parts, designing the parts, and ask for samples. Then you might need to work with finance and budgeting, because they might want to charge you for those. So, understanding what you'll be charged for from a packaging department standpoint is important. And as you work with these teams, you'll learn those things. So I just want to mention those things. Okay, stop sharing my screen for now. And we're going to go back to chapter 2 and finish going through some of the pages that we were on. Let's see. Share my screen again. Okay, so we left off. So we were talking yesterday We talked about different costs, what the total cost would be just for building a rack and what those things look like, right? Um, how quickly it adds up, and what those total costs would be. And then you're looking at, as you go through this process, can you modify something that's existing? Can you use the existing packaging? Can you upcycle anything? And what parts of your packaging are going to be totally, going to be, if you're reusing something, what parts of that packaging would be new, as well as what packs are going to be completely brand new and starting from scratch. So, and then we talked a little bit towards the end about, what happens at the end of life. End of life is when they stop making the vehicle. So I had a Toyota. It was a 1999 Toyota, and it was a two-door. It was somewhat kind of, it was a sporty kind of Toyota, but not really sporty. And it was a really good car, but it wasn't very popular because it wasn't a sedan and it wasn't a sports car. It was kind of in the middle and wasn't an SUV. So even though it was a really good car, it didn't sell very well. So after 5 years, they stopped building it. So that would be an example of a program. Once it's done, it's either done because it doesn't sell well, or maybe you have a new version of a vehicle. So, so you could either have a new version of a vehicle, or maybe the sales just don't meet the requirements to, do a new version of it. Now you've got all this extra packaging. What do you do with it? What packaging do you scrap? What packaging do you keep? What packaging do you reuse? What packaging is gone and you thought it was around, but you find out when you do an inventory at the end, it's not there. So, those are just some of the things that you have to keep in mind. Working with suppliers that, how do they call it dispositioning? How do they disposition that packaging once you're done using it? And then getting a sign off from your finance and accounting team. That's a whole process in itself, like I mentioned yesterday. Okay, so I wanted to talk a little bit about manufacturing. We've touched on this. You saw this in the video during chapter 1, the Ford Rouge plant. We talked about line side packaging and keeping things at the line, having things like lift assist, turntables, things that can help hold the packaging and hold the product, but make it easier for the operator. So we'll talk about some of those things here. So the ergonomics is something that I think we've mentioned before. You've heard me talk about the strike zone. So you will have, in many automotive companies or suppliers, you will have either an expert or a team of people that work solely on ergonomics. And they're looking at reducing injuries. Many times people can get repetitive injuries. If you've heard about people getting carpal tunnel, it's because they are doing the same thing all day. So they're, screwing in a fastener all day. So, now you have torque guns. So you saw the guy that had the lift assist, and then he had a torque gun, and he just put that assembly at the front of the truck. He was just holding the torque gun and just pushed a button versus actually taking a screwdriver or a wrench and just turning that all day long. So that would be an example of repetitive injury that will occur just from irritation and overuse of the same muscles and nerves. That would be one example. Or, stress and strain from lifting something that's too heavy. So you might have back strain or leg strain or arm strain. Those are things that can cause injuries. And that's why, as you saw going through that Rouge plant video, you heard several times where they commented, and you've heard me comment about avoiding things like bending, avoiding activities lifting, and even avoiding walking, excessive walking, because not only does that reduce the amount of time for production and slows down production, the more steps you take, and makes it less efficient, it also can cause, injuries, or it can cause fatigue unnecessarily by walking too many steps. So those are just some of the examples, weight, position, things like pushing or pulling can cause injuries. Other things too that you have would be vibration. So you might see this where, someone's working on something on the line and it's, constantly vibrating and they're touching it. That is something that can cause injury as well. Maybe being in the heat or the cold can cause some injury. And going back to vibration, you may see it some, but you won't see it as much in the plant. For vibration, for something like driving. Truck drivers, they deal with vibration a lot because the trucks, even with suspension, there's a lot of vibration. So there will be certain stations that have a lot of vibration, but as far as like full body vibration that you would see with truck drivers, for example, so that's pretty excessive and severe over time. Those are some of the things that they're trying to avoid. And again, having an air conditioned building, like they mentioned in the Ford video, those things help too, because now you're not dealing with hot or cold extremes, and you're not dealing with changes in humidity in the building too that could cause issues or dryness. I mentioned about repetitive tasks. So if the operators are doing repetitive tasks, on one hand, it gives them precision, it speeds up what they're doing, and they're more efficient. But at the same time, you have to strike a balance, because if you don't strike the balance, now you're dealing with repetitive injuries. So one of the ways that they accommodate for that is by, using special lift equipment or using torque guns, or basically work assist things that will assist them in installing parts or moving parts, or even moving packaging full of parts. And again, so there's twofold. You got efficiency, but then you got injuries. And that's another reason too, you see in many companies, but automotive, their union has it set so they have to take so many breaks, and for so long. They have to have a minimum breaks plus a lunch. And that is to reduce the fatigue. Make it a lot easier for them to make sure that they're not getting fatigued. Okay, so here's an example here of a lift assist. So you can see the operator's hand right here. And let's see if I can get this to work today. So the operator's hand is right here, and all they have to do is either push a button or clamp on it. And then they can either, probably this is going to work where it lifts it up and it takes the weight. So they're just moving it, and they're not actually using their weight to lift it. Next, we have an articulated arm. This picture is, I know it looks like they're floating in the middle of nowhere, but this is showing, if the focus is on this so you can see it. It has a pretty heavy base, so it tells you that you can get a lot of capacity for weight here. And then this goes out, so you have a lot of room. So the operator has a lot of room to work with. You have, say, bigger vehicles, you have a bigger workspace. This one is very big because it can be lifted 10 feet up in the air, and you can put it within 20 feet of where this pole is. So that is good because let's say that this needs to be put higher up on a vehicle or lower on a vehicle, instead of having the operator to, get underneath the vehicle or get on top of the vehicle, they can just use that lift assist and move it to that position. Okay, so this is an instrument panel that goes into a vehicle, right? So basically when you see your speedometer and all those sorts of things in your dashboard when you're driving. These are so large that they are put in a shipping rack, and you see how big they are. This there looks like we're only getting 6 of these in a rack. And you'll see here, the placement. We talked about the dunnage. The dunnage holds these parts in so that they don't move, and then they're far enough away so that when they are placed in, they're not hitting each other and damaging each other, because these are instrument panels. They are going to be there are going to be some class A surfaces that you don't want scratched, because who wants to get a brand new car and right across the dashboard, right in front of the speedometer, is a big scratch? So, that would be an example of something that the packaging engineer would make sure there's clearance. Again, here we talked about the transportation costs, and especially right now with transportation costs being so high, you want to maximize and get as many parts as you can on a rack and fit as many of those racks on a truck as possible. However, if you get them too close together, so on here, you probably could get, and 3 more on this rack, but in order to get 3 more on the rack, now you're probably going to risk hitting them, hitting one against the other. And now here you are back to having a scratch in front of the speedometer, for example. So balancing out, what's the best way to, ship these, what's the right quantity, how much does it cost, but then also from an ergonomic standpoint, what makes the most sense. So here, you could take this out, and let's say this looks like an instrument panel. They could be a few feet away from it. This can be sitting away from the line. They can reach in, pick that panel up off the rack, and then move it over wherever they need to for the vehicle. Okay. Okay, so we talked about ergonomics. You've heard me talk about the strike zone. One thing with the strike zone is that it eliminates the need for stretching and strains, but it also, keeps them in a limited area. So there's, there are fewer steps, less movement, and more accuracy, and they're not wasting extra steps going over to get packaging or get a part a few feet away when they can get it as close as possible. So here's an example of a tool that's used to design racks and containers. So it's called the ErgoMan tool, and it can help you, see, like, is there a problem with your design? They use this at Toyota so that they could eliminate, maybe one of the prototype rounds, because every time they do a prototype round and they have changes or revisions, now you've got to start all over again. And that whole process to develop prototypes, that can be time consuming, and it can delay the program launch. So by using a tool like this, you can see how well does this work. Okay, so here is an example. It looks like they're sitting at a desk, but they might be working on inspection or assembly of some parts that are then going to the line. But they could do their job either standing up, and the station and the packaging is right there in front of them, so they don't have to get up and move. Or this, so he's standing in the same spot doing this job. This one, they can actually sit at their job, and their line of sight, they can look at it with their eyes by looking down instead of bending over or tilting, because moving the neck can be a repetitive injury, or can aggravate something. So those are some examples where they can use technology to get a much better estimate and maybe bypass one extra round of prototyping and waiting for prototypes. Okay, so this is the ideal workstation. I highlighted strike because many times it's called the strike zone. You can see here, this is considered a non-working area. This is considered more of the ideal area because they have their arm outstretched and they're not stretching, and they're not overreaching, but they're not underreaching. Here, they are, doing some reaching here. Over here, they're overreaching. Right here, this is where they're going to do most of their work because they can move their arms, elbows right in front of them and do whatever work they need to do. So that's considered the ideal area. You'll notice here it said that the packaging is made to accommodate what they consider a 95th percentile male, meaning that most females could work in a station and would be comfortable. So, that 5% that wouldn't fit would be a woman that's really, really tall, or more than likely a woman that's really, really short. So most women can work in a station like this and not have to deal with or worry about repetitive injuries. An example of a workstation that immediately jumped out at me during that video that did not fall into this was the one that they said they call it like the basketball area. They said it was where the basketball team was because it required tall people. So rather than it falling into the 95th percentile for women, for accommodating them, it's probably more like the 1%, the first or second or third, maybe the 5th percentile. So almost the opposite, where only a few women could work in that. If you're looking at men that are over, probably 6'2", working in that area, that's going to eliminate a lot of the men too. So that's not even accommodating the 95th percentile of men. It's definitely not accommodating the 95th percentile of women. So that would be a workstation that I would guess their ergonomics team has spent a lot of time trying to come up with other ways for that work, and they just weren't able to. So they make it designated to be a special area. Okay, so here are some examples. And you've heard me talk many times, you've seen me reach into the screen. This is what I'm talking about. So you see the operators can stand here and they're not reaching, their parts are right here. In fact, this person's reach is further as they're talking and pointing than it is for whatever work they're doing. So they're doing that with the one hand, but at the other hand, they're just taking it right out of the pack. And the reason why these are angled in front of them, they probably have on this side, it probably looks like this, where they can actually install the part right onto the assembly that's passing them on the conveyor. So this operator here, one of these operators here is probably pulling parts and installing right there. And they have very little reach. And you see where it's right in front of them in the line, and their reach to wherever they're manufacturing is very, very close. But you see they have returnable bins here that they're using. And he has returnable bins here. So he's probably working on either some assembly, maybe he's inspecting parts, but he's able to take that standard bin, put it in a standard workstation for his job. And he is working from pulling the part right almost a little bit below shoulder length, taking it out, and then putting it into assembling it into whatever that part is that is used, that's right behind his arm. So yeah, so this one, it says it's a kitting area. So let's see. So that might be what's in here, but a lot of times in an area like this, you might see kits. So what it is they, he might be putting the kit together, or he might be taking that kit and using it to install the part. But either way, these kits are coming in with parts, but for whatever reason, they determine that it is more ergonomic and more economic to get the parts in and then assemble them in the manufacturing facility, whether it's the OEM or the tier that's receiving it. And part of that, it could be easier to put together. An example would probably be, again, in the Ford video where the man had that lift assist and he pushed that whole assembly into the vehicle. They could have probably broken that assembly up, and I'm sure at some point the original process was to break parts like that up into individual parts and then put them onto the vehicle individually. That probably took a lot more time to do that. You saw it took him literally 10 seconds to put it on and torque the screws. And then he probably spent another, 20 or 25 seconds pulling the part over with the lift assist and sticking it up there. And then there's probably another 10, 20, 30 seconds where he's walking to get the next part. So that whole cycle was about a minute, but it was an assembly. So this is an example of a smaller kit. And it's easier to have everything in one tote already put together so that they don't have to go get, screws. Now, wait, now I need to have 8 of these fasteners. And then, oh, wait, I need 12 of these. Oh, okay, wait, now I need this component. And instead of them, walking or getting them all from, 4 different bins, they can put them all in one bin, and it's a much faster assembly process for them. So they found that it's easier to have someone in another area putting those parts in the bin in the order that they need them. And then that bin goes to the line and they put it together. So all those activities are faster than if the operator had to put them together on their own. Let's see. Okay, so this we talked about a little bit before. Visual management. Visual management is a way to let people know what the standards are, or for things to stand out if they don't follow this visual management cue. So you can have a couple things. You can have colors, like the stripe on this tray here. This might be a part that's, many times you have what's called the left-hand part and the right-hand part. So that would be similar to like the passenger side and the driver side, right? Or you might have, something underneath the hood where you've got the same 2 parts that are mirror images meet up together under the hood. So one they call the left-hand side, one they call the right-hand side. But if you accidentally get 2 right-hand trays, now you can't put your part together because now you've got 2 parts that are the same versus having 2 mirror images that would meet together. One way to do this is to do things like color coding the trays. I mentioned during the Ford video, if you notice the floor, they had markings with yellow tape. Some things were yellow tape on a step stool so that people knew, hey, this is trip hazard. Notice that this yellow square is elevated so you don't trip. But many times it is to designate that there is something missing or something that needs to be done. So if you see a square that's empty, that means there's probably a tote or some equipment that needs to go there. That's its place and it's not there. And then you have to deem, okay, determine, is is it okay that this is empty? Is it supposed to be empty right now? Does that mean whatever equipment it is in use? Or is this a cue for a delivery driver to bring more parts or bring the equipment, whatever it is that's needed? So visual management is used for things like that. But one way you see again is by seeing stripes on the trays. So the right-hand tray might have a blue stripe, but then the left-hand tray for the left-hand parts would have a red stripe. And that way, the operator that's working on installing the one on the right-hand side, if a tray shows up with red, they know, oh, that's the wrong part. So rather, they may not even know until they try to put them together. It may be hard to tell what they know that they look that way. It also helps on the supplier end because that tray, even though they look the same, they might be a mirror image and you cannot put, sometimes you can't put the left-hand part into a right-hand tray. They might, injection mold something or thermoform some feature on this tray so that if you put the wrong tray, if you try to put the wrong part on the tray, it won't fit. So then they can look and, oh, wait, we've got blue trays. We really should have red trays. So like I said, visual management, that's a lean manufacturing process, and it is used throughout automotive to help operators, differentiate between a good part, a right part, and an incorrect part, or let them know where a particular part is supposed to go. So they know, oh, wait, if it's in a blue tray, it always goes at station 14. If it's a red tray, it goes at station 15. So just very easy, quick ways for people to remember and notice that, something is wrong, and keep them on track. Okay, so I've mentioned this many times. When this packaging is designed for line side, the whole point is to reduce or eliminate as many steps as possible. And when I say steps, I'm talking about physically walking, because let's say the operator walks back and forth to do their job because they have to go get something from here. But if everything they need is put in the same spot, then it saves time because now maybe they're only walking 5 steps instead of walking 20 steps. With those left-handed trays versus right-handed trays, for example, if the blue trays are at their station, then the red trays are at the other station. They don't have to walk over and get the other trays. So it saves a lot of time. They also list here some parts that are that utilize color coding. I mentioned like the left-handed parts and the right-handed parts. These could be things like door handles, passenger seat versus driver's seat, things like that. But then also options. So, things like air conditioning versus no air conditioning. So you all are probably like, all cars have air conditioning, but someone like me grew up at a time when you had the roll down windows. You may only see that in a rental car, but all the cars had roll down windows. You had to roll them down by hand. And then you didn't have air conditioning. So you're driving on vacation or on the highway in the summer, and the only way you can get air conditioning is by rolling down the windows. So just imagine being on the freeway or the highway going 60 miles per hour, and it's really hot, and the only way to cool the car off is to open the windows. But I digress. So things like the radio, different options on the radio, is the car gonna have a sunroof or not? Those are some things that can help, using trays or using visual management, not just trays, but visual management really helps. So again, you've got color-coded bins, right? I mentioned before that there's not been a lot of success with that in automotive. but usually the lack of success comes from just trying to just have this for multiple suppliers, or maybe you have, this particular tote, and in this tote you have this dunnage, but then you have another part where you only have this dunnage, right? What happens is they found that they thought, well, if we color code these, then the pink ones will always have the two pieces of dunnage, and then maybe the blue ones or the green ones or whatever other color would have just the one piece of dunnage in there instead of two. But if it's not managed well, you might get someone that takes that dunnage out, throws it away. So, or they might just take that pink bin and send it to the blue bin company, like I mentioned before. So another reason why, you're going to see this color coding is, there are a couple different reasons. So you can reduce the amount of inventory as well. So you can get smaller trays. You can have the tray that matches the amount of product that you're using. So even if you're building, 500 cars, you still need to have, the right hand versus the left hand. So this is one of the ways to bring the parts as close to the operator as possible. So if you have something like those trays with heavier parts, you're probably going to have lift assist for that. But you notice that when we looked at those pictures of the workstations, they were using the smaller handheld totes. So that is one way that parts are taken and moved over as close to the operator as possible. When I mentioned before, it's really important to work with your engineering team, manufacturing engineering, and your manufacturing staff, and understand how much room is on the line. More than likely, they're going to, the manufacturing engineering team is going to push for smaller totes because they can get parts right in front of the operator and keep the operator from, reaching or walking or moving or waiting for parts, that kind of thing. But also keep in mind, this is talking about inventory. So top hats, I know you saw top hats when we looked at the video of the Ford Rouge. It allows them to bring a bigger pack of, or a stack or a pallet unit load of parts close to the line, but then whether it's that tray or that tote, so you might have a pallet full of totes. They might just take that, they might need 3 an hour, or 6 every 2 hours. They can take those totes and just put the smaller totes on the line, and then they can actually replenish, so the route drivers can come back and replenish the racks much more quickly. They may have to do it more often, but instead of having to take that whole pallet load, that unit load, driving it back and forth, or going to get a few from that pallet and bringing it out to the line, they can take that unit load, sit it next to the workstation, and it can be replenished a lot faster. So, those are some of the things you might see. We talked about sequencing. So this also, by having smaller totes, it allows for sequencing. So you generally don't want to see where you have multiple parts in the tray. This probably would be put into, instead of a tray with 6 different parts, you probably have 6 totes on the line with, each tote has a different part in there. But they would be, you'd have these smaller quantities, and they could put these, few on the line instead of putting all these, and they don't necessarily need them all. They can pull what they need from that bin as it's needed. So they can say, we know for the first hour, we're going to run through this part. so we can put some totes of this part out. And then we know as we get close to the end of the hour, we'll start replenishing that line with this other part. So when they do that, they can still keep all that on the line side, but they keep everything they need, but it helps them with some of those JIT orders, those just-in-time orders that we talked about. We're going to go back to that 2 hours of material. So that was one of the homework questions. The route drivers know they're going to be going back to the same station every 2 hours. So it's kind of like a bus route. They know that at certain times they're going, or a shuttle, that every so often, every 2 hours, they're going to be going back as a general rule and dropping off more material and picking up material as well from or I should say picking up empties. So the material they're picking up will be empty packaging, and they'll be dropping off full packaging with product in it. So the material they're dropping off will be parts in packaging. The material that they're picking up and that they're taking away, that they're leaving with, will be empty packaging. And they plan to do that, every 2 hours. So if it's an 8-hour shift, roughly they're going to do it 4 times during a shift. We talked about kitting. So kits are good for assembling things on the line very quickly and having everything right there, almost ready, but you do the final assembly. However, there is another step that's back before that the operators aren't concerned with, that they are taking these parts and they're putting together an area for kitting. So they have a whole different section where they're doing what's called kitting. So they're taking the, different packs, and they're pulling, part A from here, part B from here, and putting part A and B together in a kit. So they actually have a mini assembly operation or partial assembly operation in those kitting areas. They talk about sequencing. So sequencing is great for the operator because they just know that I pull 1, 2, 3, 4, 5, 6, 7, right? Whatever that order is, or they get a bin or handheld tote, and the parts that they need from that tote have been put on the rack. So it's in front of them when they need it. And then the next rack may have a different part in it. Instead of having all this, they would have, say, 6 different totes. And those totes can go line side. Okay, so this one I touched on a little bit. Part density decreases if the parts are handled with ergonomic assist arms. So for the same amount of parts, you're going to need more racks. So on one hand, that's true. Go back to this. I mentioned before that you might be able to get more of these panels on a rack if you put them closer together. But then you're dealing with, are you going to get them scratched? And then if they're heavy and you use a lift assist, it may not be as accurate. So the chance of you scraping the part that's next to it, or, as you pull it up, that could be, a hazard. So again, while they're using lift assist, it can help. But you definitely need more clearance for those, whatever those parts are. Another example would be, if you're using the material handling equipment, a lift assist or anything like that, small cranes, whatever it is, you've got to have more clearance. Another example of having to have more precision on a pack, not exactly the same, but the reason would be, say, if you are feeding in parts that are installed by a robot, because the robot is programmed to pick from a specific area. And if the packaging, for whatever reason, is not repetitive, or it's not precise, then the robot will have trouble locating. They won't know where to go. They're like, well, I thought it was over here, but it's not. It might be over an inch or two. So that robot will keep missing that part and won't know what to do. So it can also decrease the density, because you want to make sure you have accurate placement and you have enough clearance around those parts so that the robot doesn't get confused by other parts. Okay. All right, so I'll get into this a little bit. We probably won't get through this today because I do want to go through the homework briefly, but critical dimensions. This is really important for parts. So you'll see in automotive that you may get a dimension drawing, or you may be able to go in a system and get a drawing and see what the part dimensions are. Many times you will have parts, part drawings, but you may not have parts. When you're starting to develop packaging, or your suppliers developing packaging, they're doing their best guess and doing an estimate based on what the drawing says. So there may be fine details that you are not able to really confirm until you have prototype parts and prototype packaging. But one of the things that automotive does is they try to be very, very precise on their drawings so that it can be used as much as possible to represent the part. So sometimes you will hear packaging suppliers asking for math data. They're looking for the 3-dimensional files that will show what the part is. It'll show out the dimensions. They can simulate, they may have software that can simulate what the pack would look like with the part in it and simulate what that clearance is. So it's not foolproof, but it can eliminate one of the steps of prototyping. So we talked earlier about, ways that you can digitally determine what a workstation looks like, and that can affect the part design, it can affect the pack design, but it can also take a step out of that whole proving out, building, pre-launch builds, pre-production builds. You can reduce that many times. And the same thing with using these critical dimensions. So critical dimensions are used for, like I said, 3D drawings. They have standard ways to draw those parts. It's readable if you're in packaging. However, the standards and the tolerances are not the same as a packaging drawing. But if you can read a packaging drawing, you can read this. So they talk about the tolerances. The tolerances are important because if you have a part that is plus or minus 1/4 of an inch, then you could build and you get a part. Let's say the tolerance is plus or minus 1/4 of an inch, which means that there's a 1/2 inch swing for the part, one way or the other. So one part could be 1/2 inch bigger. If it's on the high side of the tolerance, it would be 1/2 inch bigger than a part that falls at the low end of that range, if that makes any sense. So it's important to understand what the tolerances are for the parts, because if you receive a part and you design it based on the part or prototype sample that you have, and you don't know what the tolerances are, you could say, I get this part and it's 1.25 inches, and you make the packaging design to fit 12 parts because you can fit 12 parts that are 1.25 inches. But if you find out that this part is on the high end of the tolerance and you try to put 12 in that same bin, now you maybe can only get 10. And you may not understand why. Well, what? This fit before. This is what I was told. but you have to also look at the tolerances and understand what the tolerances are for the part. And tolerances, that variation is normal because nothing is 100% precise. So it will be variance in everything. I had an example I was going to show you of that. Okay, so these are just different materials that were 3D printed. And you can just see the whole point of this is to show, with the different materials, they have made a shrinkage or something like that. But these parts are all supposed to be the same size. And I'm going to put this up to the video so you can see it. These parts are all supposed to be the same size, but you can see that this one is clearly smaller than this one. And if you turn it that way, you can see how big of a discrepancy there is even in the length when you put those together. But these parts were all 3D printed from the same pattern, and you can see there's definitely a difference based on the material. So it's important to know what those tolerances are, because if you are on the height of the tolerance and you use a pack, you design a pack based on that, it may be, the parts may be loose in there. So you kind of have to understand, how do the parts need to fit? What is the tolerance? How much of a gap could there be? And is that going to be a problem? And then building something to accommodate for both of those. This is just showing how the diameters, when you measure the diameter, what your plus and minus are. You got the 14.02 and 13.99. So that's like your plus and minus. So here it is, 14 inches plus or minus 0.02 inches on one side, but then it's also a minus 0.01 on the other side. So that means that, the first number is the high end and the second number is the low end. So this could range anywhere from 14.02 to 13.99. So that's the 14 plus the 0.02 and the 14 minus 0.01. So that's the high end of the tolerance and that's the low end of the tolerance that's allowable for that part. So this talks about here, if the diameter, this is for a wheel, right? There's measuring this wheel. If the wheel diameter that's drawn is too small, the tire won't fit. And then the packaging is the same way. So on the drawing, you are going to see like the critical dimensions. One thing I've noticed with the automotive packaging is, I'm sorry, not for automotive, but automotive parts. So for packaging in general, you'll see a length, width, height, and there's a plus and minus dimension for each one. But for automotive parts, many times you will only get like a length and a width or a length and a depth. You don't always see, it's very hard to see all three dimensions. And part of that is, that's their style of dimensioning, but part of it too, if a competitor gets their hands on this drawing, because the drawings, can tell them a lot about what they're doing. So they don't want the competitions to get a hold of this. One thing I want to mention is in some industries, not just automotive, I saw this in computers too. They, instead of using in automotive, the vehicle, so this is going to be the new SUV to replace the, old SUV Super Duper, whatever it is. They don't want people to know what they're building, yet, what to do that's coming out and any innovation or changes that they've seen. They don't want people to know ahead of time because maybe the competitor might do a copycat and get it out first, or for some reason, customers might like that second version better. So, there's a little bit of competition. There's a little bit of confidentiality going on with those dimensions. So you'll see many times where with packaging, you'll see length, width, and depth. You will only see the length and width, for example, on a lot of the engineering drawings. Another thing is some of these drawings you'll see, they will have dimensions for angles. So if you have something, so we'll just use this, right? The drawing for this reader, they may not say the length of this part, but what they'll do is they'll say that this angle here, it needs to be at this angle. And then, maybe this needs to meet at a certain length or something like that, or this needs to hold the computer. They'll have some of those dimensions about information on the dimensions to help you to build or for people to build those parts, for the supplier to build those parts. But from a packaging standpoint, you just need to know, like, how tall is this thing? And you may not be able to find out how tall it is from looking at a drawing. This is an example of a machine that will actually measure the vehicle. So that's partly how we know what the precision is of these vehicles. So, something like the way this wheel well fits on the vehicle, or the way the windows fit, because if they don't meet tolerance, you may have issues rolling the window down. It might get stuck, or you might not be able to, you roll it down, but maybe you can't roll it back up because it's just slightly out of tolerance. It might be on the high end of the tolerance, so the window shuts a little bit this way when it rolls up instead of rolling up this way. It's a little bit too big, so it maybe goes out, flares out, as an example. But these sensors are very accurate, and this can help them to know, the manufacturing engineers that are working on vehicles, to know how accurate these, the parts are. Because something like this door, you don't really pay a whole lot of attention to it because it is in tolerance and the fit is very, very close. But if this were out of tolerance, whatever they deem it to be, the unacceptable point for that part, visually, you can usually see that this is crooked. And they, in the automotive companies, generally don't sell cars like that. So they're very big on how the panels and doors and everything fit together. And these high-tech machines measure that. Okay, so that's a CMM. This is another CMM. So if you compare the two, this one is handheld. This one is robotized. And it can send the information back to someone's computer. Where with this one, you see she had her computer right there and was feeding into the computer. So there are a lot of different versions of it. This one, the operator's taking a picture of it, and then it can draw, that information as far as what the size is and is it in tolerance or not. And then they can use computer with a 3D imaging or math data to, look at any flaws or anything they might want to change, or maybe they've started to do some of these build events and they can't get another part to marry onto this. Then they can take those pictures or scan or check any of those things and see something's out of tolerance that they weren't aware of. Let's see. Trying to see. Okay. I want to get through the homework too, but this is an example of when the CMM is used and it measures the car. This is what the output might look like. So when it says nominal or nom, that is telling you that is what the middle number is, or that's, you know, what they're shooting for. And then this will tell if these parts are that they measured, if these points are in range or out of range. So you can see here, this one was out of range. So it was 143 millimeters plus 0.7 minus 0.7, so plus or minus 0.7 millimeters, right? But you can see that it was 0.75 millimeters, so it was out of tolerance. So when you look here, you see 143 was what they were shooting for, but when they actually measured it was 143.75 millimeters. So it was out of spec. This one that's yellow, it passed, but it's really close. It's right on the edge. So this helps them understand, you know, are the parts being built according to spec? Are there any issues where they're not meeting spec? Or even these were sent out to us from our tier, and now that they came in, we double check them. They're not in spec. Could it have been that there's some design flaw in their manufacturing process, or could it be that maybe this part got deformed? Is the packaging performing properly? So that's just something, you know, those are things that from a packaging engineering standpoint, this is an example of how you could use this information, how this tool could help from a packaging standpoint. So this is saying that, you know, shipping racks they don't use this process to measure with CMM. This is how they determine the dimensions. So you can use this process to measure them. So, you know, look at your critical dimensions, and then you want to measure it on the CMM. So you want to make sure that they fit in the rack. You want to, you know, get a rack, get ready to test it, put the parts in, the parts that you measured, and then you want to put them in 3 different parts, you know, those parts at different locations in the rack to make sure they fit. And then you test the rack, move it around with the parts in it. And then afterwards, you want to remeasure those parts with the CMM. So instead of measuring the rack, you're measuring the part to see did the parts get deformed, were the parts protected properly by the rack. And then if they are getting deformed and they were in tolerance, but now they're out of tolerance, and you find out, okay, they were the one that was on the last and on the left end of the rack every single time on the bottom, that's the one that's always deformed, or the one on the top in the middle is always deformed. That tells you that that's probably where, well, that's where you need to look at redesigning on your rack or making some revisions to the rack to protect your part more. Besides dimensions, you know, we talked about this before, we've got classes, class A, class B, class C. Generally, class A surface is what most packaging engineers and most part engineers are most concerned with, because class A surfaces are going to be most visible, the customers are going to see them, or it could be a part that's precision, like, you know, a machined part, like the machine head on the engine. If that machine part is out of tolerance, or maybe you get scratches on that engine, it can cause issues with maybe, you know, performance, or, you know, that might make your engine, that's where you would hear an engine knock, for example. But from a consumer standpoint, if you see something that a class A surface that's scratched, visually, that can turn a customer off. So you've got 2 things. You've got the function and you have aesthetic that are considered class A. Um, Class B would be something that is not seen, so maybe something that's underneath the vehicle. They mentioned a windshield. Class C is something that the customer may never see. And it's not important, you know, from a visual standpoint. But sometimes some of these parts under the car, they may be prone to, you know, moisture, so they may not want to get them wet. So when they do the packaging, they'll tell you pack with, you know, desiccant or VCI packaging to protect it from water. They don't want it rusted. Even if you go through a car wash later, it will maybe get rusted. So, but starting off, coming right out of the production line, they don't want those parts to be rusty. So this talks about here, like if you have a Class A surface, you don't want you want it to be held, you want that part to be held in such a way that it's not going to touch the Class A surface. So I'll give an example here. So for example, maybe this is a Class A surface, right? When you put this in a pack, maybe you're holding it, the pack is holding this part of this part. So this is not going to have any contact. There's no chance for it to get scratched during the shipping process. Let's see. Another example would be when you have things like brackets. The brackets can either, you don't want the bracket, you want the brackets protected so they don't break off, or you don't want the brackets to maybe rub against a Class A surface. So those are some examples of, you know, what you might have. And this would be up to the product engineer to determine, is this going to be an assembly that's put on later, or is this going to be put on, will this be attached to the door frame when it gets there? So this just talks about, you know, building that sheet metal part and, you know, what gets attached to it and what doesn't, whether it's Class A. And you need to understand these things because when you build the packaging or put the packaging, you need to know, you know, where the sensitive spots are on the part. Is there something that if you put two parts together in a pack next to each other, will they damage each other or do they all need to be separated? So you can see there are a lot of spots in some of these packaging here, like this, in this packaging, this is keeping the parts separate. This is keeping the parts separate. So, you know, these might go into a pack like this. So, and they're all facing maybe a certain direction, which helps for one, it keeps, say, a bracket from rubbing up against a Class A surface, but it's also, they're presented the same way to the operator. The operator can just pull it out and do whatever install they need to do. So it helps with ergonomics, it helps with efficiency, and it also helps with damage to the product or preventing damage to the product. Let's see. I just want to see how much more is here. I think I'm going to stop here at standard container fabrication. And I want to go through the homework really quickly. We've got about 15, 20 more minutes. So I'm going to go through that. Ignore my big print. One day your eyes will appreciate bigger print. I'm going to make it a little bit smaller. Okay, so answers homework 1. So I'll post this, but I want to go through it. So first of all, a couple things. So the first one was asking about how much space is taken up in a trailer with, you know, 400 trailers. That was the number for 400 truckloads that would come in for a day's worth of material into a plant. And then from that, those 400 trucks, what's the square footage that it takes up to tell you how much square footage you need inside the building, to how much space you need to put 400 truckloads worth of material into the plant. And you don't have to worry about the height, because you can assume that if they're stacked 2 high or 3 high in the trailer, there's enough room in the plant to stack that high as well. So you're really just looking at your square footage for this one. So again, you're looking at the trailer, which is 8.2 feet wide, or 98.5 inches by 52.5 feet long. And that was from your listed in the standards on trailers. When you look at that standard, one of the things I noticed is that, and I even did this at first, that 53-foot trailer, it says it's 52 and 6 inches, and some people are saying 52.6, but it's really 52.5. So you're just going to take that area of the 8.2 feet for the width of the trailer by the 52.5 inches wide to get 430.5 square feet. So that is the square footage of one truck. And then you know that 400 truckloads of material are coming in, and that came from the chapter reading. And these page numbers changed a little bit because I updated it, but it's in chapter one reading. So you can take that 430.5 square feet, that is the square footage of one trailer, and then you're going to multiply it by 400 trailers to get 172,200 square feet. So, you know, this is by looking at the sheer amount of space that you need just for one day's worth of material. This is why assembly plants really push for, you know, being able to work with JIT. They want their suppliers to bring things just in time or bring in the sequence material, because instead of bringing in, you know, like a bin of all of these, for example, and they only need, say, 4 of them. If they sequence them, they can get 4 of these in a smaller tote versus having, you know, 20 of these in a bin. So they can manage the size of what they need with smaller packaging. Okay, so the next one is talking about, this came from the video, where the question says about, you know, how much time does it take to run the, you know, make one vehicle. In the video, they said it takes about 1 minute. The cycle to build one truck was about 1 minute. So that would be the short answer. But if you wanted to get fancy and calculate, you can say, well, they had 72 cars per hour, which was in your reading. And the car, you know, the car comes off the assembly line every 60 seconds. So you can take 60 minutes, 60 and divided by 72, it's going to take just under a minute, 0.83 minutes to make a vehicle. So again, you can take for every hour, 60 minutes divided by 72. That's going to tell you how many minutes it takes to make a vehicle. So 0.83 minutes equals 50 seconds. So if you take the 0.83 times 60, you're going to come up with 50 seconds. So all the workstations have to run in sync. So all the workstations, the cycle is going to be like 50 seconds. And they mentioned they had a buffer in case they, you know, have a slowdown or something. They mentioned that as well. So that's where they said it takes about a minute, because they know that the calculation is 50 seconds, but they add a little bit, you know, just to give them a little bit of breathing room. Okay, so the third one, batteries are considered tier 1. So it's a part that is made and shipped right to the OEM. The next one was a few hours. It has how much material was kept on the line, kept line side, generally a few hours. So a very, you know, general answer. So the next one was talking about the different types of trays and their pallets, I should say. The pallets that I have to look for that exact question, but the answer was no, because that style of pallet did not have a bottom deck. And if you put that pallet onto a rack that didn't have support beams, then you couldn't get it out with a fork truck. And then it doesn't really have any strength either because there's no bottom deck to it. Okay, so equipment taking up valuable space in the pick faces, or, you know, in the aisles, on the floor when they're not needed, those are excess containers, right? The key is to try to keep the amount that you need of product in the containers. So let's talk about right sizing. And then also, you have the route deliveries. You want to keep those off the floor. When they're empty, you want to take them away. When they're, you know, gonna be used, put out what needs to be used when it needs to be used. Okay, so a monument is a stack of pallets or pallet loads on the floor and in racks. So I think we saw this in the Ford Rouge video. At one point, there was like a wall where you could see all these, you know, bins that were stacked up against the back wall, pretty high. That would be an example of, that could be an example of a monument. If they were using them right away, probably not. But if that was kind of their regular storage and using that as a warehouse location, and they never really didn't pull the material as often as to match the titles, that could be considered a monument. This one was talking about, the question was, can you allow or can you have more than one part number in the same tote? And the answer was yes. You know, so the statement was you saying something like you can't have multiple part numbers in a container, but you really can. It's not practiced very often. You'll see it like in kitting, or when you have sequenced parts, you'll see multiple parts with, you know, part numbers in the same tote, but it's not a common practice. If you do see it, it is, there's a purpose for it. It's either like something sequenced, or you know, there's some reason why it is, and it's clearly marked. You might have visual management, but there's something that will alert the team to know there are multiple part numbers, so that what you won't see is, you're not going to see things that look almost identical in the same tote right next to each other. So if you see, like in a kit, say you see a left hand and a right hand right next to each other, they're going to be clearly marked, and they're going to always be, the left hand will always be on, say, on the left hand side, or the top of the bin, and the right hand might be on the bottom of, or the right, you know, it'll always be in the same spot. It's not like they're just going to be thrown in there together, and you're going to have, you know, which one is the left hand part, which one is the right hand part. It will be clearly marked. So when you have multiple parts in the same tote, there will be plenty of, you know, signage or labeling or instructions so that they aren't confused. And then the last question was, you know, if they mentioned in the video what the defect rate was, that it was 0.1%. So that the question was, how many trucks will you see with the defect while they run production? The defect rate is 0.1%. So 0.1%, if you convert that to a number, is going to be 0.1 over 100. So basically, the number and a percent. So percent is basically a fraction. So let me get my handy dandy annotation out here. I'll just write text here. So let's get a color that you can see. Okay, so if you've got 0.1%, right? Or let's just say, let's pretend that I actually wrote that. Okay, so 0.1%. percent is the same as, it's basically per 100. So that's what percent means, per 100. Okay, so then you take this number and you put it on the top of the equation. So basically percent is an equation. So you have the, I'm just put it back here. So you have a 0.1 per 0.1 per 100. So that's what you have, 0.1 equals 100. And I'm gonna pull up my calculator. We have 0.1, and you can either say divide it by 100, right? So I did divide it by 100. Let's just pretend I am not hitting my finger twice on it. Okay, 0.1 by 100 equals 0.001, right? Okay, alternately, you can do this. You can go 0.1 and then hit your percent and you get 0.001. So that's another way to do it. But that's what your calculator is doing. It takes the number that's in front of the percent and then it divides it by 100. So if you do it on your calculator, you put the number divided by, so we'll just say 3% equals 0.03. So you can either do 3 divided by 100, or you could just hit, 3 and your percent button on your calculator to get, you get the same thing. So now you take that 0.001, point equals 0.001, times 1,000, because they make 1,000 vehicles a day. And that's how you get one. So they, at one vehicle a day will have a defect that doesn't meet the specifications that they reject. So I hope that helps. I hope that makes sense. So again, remember, you can either do the 0.1, hit the percent button on your calculator, or you can say the number here, 0.1, divided by 100, because that's all a percent means. Per is divided by, and then the cent is 100. Just like if you have pennies or, anything like that. 100 pennies is $1. So 1 cent equal, 1 cent is the same as 1%. 100 pennies is $1. So 100 cents is $1. That's where that comes from. So that is the homework. I hope that was helpful. I will be posting assignment 2 today, so you'll have that. It'll probably take me 2 hours to get this to load, as always, but I will post this today. And always, any questions, any concerns, anything you think of, let me know. I'll also look and see if I have any supplemental information, just as an FYI, for what we're going through in chapter 2 that might be of interest to use. Won't be on the homework, but it's something that if you decide that you're going to work in automotive, if you get a job in automotive, it's a great reference tool to use to look at the standards. So I hope that was helpful. Again, tomorrow I will finish up chapter 2. I will post your homework tonight, so you'll have that. Homework again is due Monday morning, next Monday at 10 a.m. And questions, comments, like to hear what you think, what you're thinking about this information, how you're applying it, because even though this is automotive, it definitely is, very similar to industrial, the whole process of designing for manufacturing, the lean manufacturing processes, that's a lot different for industrial and automotive packaging, versus say a food or consumer goods, because consumer goods and the foods, you're looking a lot at like consumer, what the consumer wants. You're looking more colors and the feel. This is more functional, cost oriented, whereas in consumer products, you're focusing on the cost, but it's more focused on like, what's the cost of this so we know how to price this, and how can we make sure that the pricing is in line for what the consumer is going to buy. This is more, it's utilitarian. We want this packaging to be very useful and help us in manufacturing, help us in shipping, protect the parts. So they are very cost conscious, but the cost is worth it if it meets the criteria. So it's important to have standards. It's important to have criteria clearly lined out for your packaging in automotive and industrial packaging, and things like safety, ergonomics, manufacturing time, speed. Those things are very important as you go through the whole process for developing packaging and launching packaging in these types of environments. So again, I'd like to hear feedback. So, just post, any questions you have, send me emails. I'd love to hear from you. All right. So that is it for today. So tomorrow we'll have our next lecture, and, let me know if you have any questions. All right. You guys have a great day.